One of the places that Boolean algebra is used is in the design of gates and circuits. And because Boolean algebra can both describe and design circuits, and circuits are made up of gates, some combination of gates. And the way gates work is they have inputs, and those inputs are either on or off, and those can be directly related to the ones and zeros that we use in Boolean algebra. Gates also have outputs, and the outputs are either on or off. Again, can be directly related to the ones or zeros that we use in Boolean algebra. So here are three of the really basic gates. There are more gates, but this is three of them. There's the AND gate, and the AND gate has two inputs, and the output is the multiplication. It's the same as, it's an AND, which is the same as X times Y in Boolean algebra. So this is the multiplication in Boolean algebra. There's an OR gate, and this is represented in the Boolean algebra addition operation. And there's an inverter, also referred to as a NOT gate, and it is the operation that we call complement in Boolean algebra. So those are the basic gates, and to make a circuit, you combine those basic gates together. You need to have inputs, and in the tool we'll be using, those will look like switches, and you need to have those gates, and then you'd be able to connect them together. And then add a light bulb to see the results. And depending on what tool you're using, whether it'll use a light bulb or something else to identify whether the final output is on or off. When you're doing this, order of operations is important. It's always important, right? If you get out of order, if you do things out of order, you can end up with the wrong result. There are several free online apps that are available to do circuits, and you're welcome to use any of those that you want. The one that I'm going to be using is Logic.ly with a dot in it, and I'm just going to be using the free version. I recommend if you use that you do use the free version. It'll do everything that we need it to do. So let's go ahead. Here's an expression, right? Here's a Boolean expression, X times Y plus the complement of Y. And let's go see what that looks like if we make a circuit out of it. Here's the app that I'm going to be using. And X, Y, I'm going to copy that expression here so we have it right here with us. And to do that, I'm going to do a label. So when you when you do a label, you do it right here. And our expression is X, Y plus the complement of Y. And you definitely can't do an overbar in these. So go ahead and use the single quote. All right, so that's our expression. And notice that the expression has two variables, X and Y. And so we're going to need two inputs. So here we're going to use the switches for an input. We're going to have one for X and one for Y. Notice you just grab them and drag them onto the right side, and then we can label them so we can keep track of X and Y and know what they are. So I just bring a label up here by the first one and type in X. Then I drag a label down here by the second one and type in Y. And there I've got the two inputs, and they've been labeled X and Y. All right, so I can start with that. Now I want to do order of operations, so our complement operation will happen first. And if I go, oops, that's not what I wanted. I wanted to slide. There we go. So what I need for a complement is the NOT gate. And so I need NOT Y, so I'm going to put this right after Y. And that's how I get it, is I take Y, the input Y, and I have it be the input to this NOT gate. And that means the output of this will be NOT Y. So there's that. The next thing I'm going to do is this multiplication, X times Y. And multiplication in a circuit is done with AND gate. So I'm going to use this AND gate here, and I need one input to be X and one input to be Y. And that's the X times Y is that AND. And then I need to take the output of the X times Y and the output of the complement Y, and I need to OR them together, right? We have an add in the Boolean algebra, and in a circuit, that is the OR gate. So the OR gate for addition, the NOT gate not the AND gate for multiplication and the NOT gate for complement. And now I'm going to take the output of the X and Y, and that's going to be input into one of the ORs, and then the output of the NOT Y, and put that in, and then I've got those combined, and that's really everything right there, right? So now I need to see what my output turned out to be, and to do that, I'm going to attach a light bulb. So there's a light bulb, and I just put this on the end, and I connect the output here to the light bulb. Now notice the light bulb is on. Both the switches are off, so when both the switches are off, the light bulb's on. If I turn on Y, then the light bulb's off. If I turn on X and Y is off, the light bulb's on. If I turn on X and Y, the light bulb's on. Now that we've got this circuit made, it's a good idea to verify that we did it correctly. So we know how to work with tables, right? So here's the expression X and Y, or X times Y plus the complement of Y. And here's a table where I put the value, all the combinations of X and Y, then did each part of the operation. So the NOT Y here, and the X times Y here, and then the last one is the OR operation, X times Y added to the complement of Y, and that gets the result. So now when they're both inputs are off, I expect 1. When X is off and Y is on, I expect 0. And when X is on and Y is off, I expect 1. And when they're both on, I expect 1. So the 3 ones, we expect the light bulb to be on, and the 1, 0, we expect the light bulb to be off. So let's go verify that that's the case. So when they're both off, we expect it to be on. Sure enough, that's a win. When X is off and Y is on, we expect it to be off. There it is. There's that 0 we were thinking of. When X is on and Y is off, right? X is on and Y is off. It's on. That's the one we were hoping there. And when they're both on, the light bulb is on. So that's that one at the very end. So we've been able to verify that the circuit is doing exactly what we expect here. And we were able to verify that with this table. Another way we could verify it, the other way that we could verify it is to just substitute zeros and all the combinations of zeros and ones to this expression and then compute what that end result is. So a couple of different ways to verify that our circuit is working the way we expect it to.